Okay, it seems we are right.
Yes.
Okay, great. Yeah, just wait for 1 minute and then I guess we can get started. Okay, hello everyone. Welcome to the second lecture of PNS Modern SSDs, Spring 2023 edition. So today we are planning to discuss NAND flash read-write operations, the topic actually that we couldn't cover in the previous meeting. And also we are gonna see how we can do sensing in NAND flash chips. But before that, I would like to remind you about one of our, the new seminar, which unfortunately the date is wrong on this slide, but it's going to be on March 29. Dr. Hayu Bao gonna discuss about GenPip, her work. So the link to the YouTube link here is correct one, but so the date is not October 19th, it's March 29. I would love to invite everyone to attend that seminar remotely or in person. Okay, so for today's agenda, as I said, we are going to see NAND flash page read write and also sensing circuitry. Let's jump into NAND flash page read write. So as a quick reminder, a flash cell basically is a transistor that it has, gate, source, and drain. And you know that in order to turn on a transistor, you need to apply voltage between gate and source. And that voltage should be higher than the threshold voltage. So, and then, the transistor is going to be on and you can, and it can basically flow the current. So the difference between a flash cell and a normal transistor is just a special material that we have in 2D NAND flash cell, as we call them as floating gate, or charge trap in 3D flash. So the functionality of this floating gate is just to trap electrons so that we can have higher voltage thresholds. So whenever you want to program a flash cell, you need to apply a high voltage. And with this high voltage to the gate and substrate, with this high voltage, you will basically move some electrons from the substrate to the floating gate. And those electrons are going to be stuck there. So because of these, let's say, negative charge that you have in your gates, you need to apply a higher voltage, the gate source voltage to turn on the transistor. Or in another word, basically the threshold voltage is higher when you program a flash cell. So in order to see that your flash cell has been programmed already or not, what you need to do is just applying a reference voltage. And that reference voltage should be something between the normal threshold and the high threshold voltage, which we have that when we program a flash cell. So by applying that reference voltage, if your flash cell, is on, means that basically the threshold voltage is the nominal one, and you haven't programmed the flash cell, and it's already erased. But if it's off, means that the threshold voltage is higher, means that you have already programmed your flash cell. So with that, you can easily understand that, what is the threshold voltage status in your flash cell. And basically, we can encode that status as 1 and 0. Basically, when the threshold voltage is the nominal one, you can encode as 1. And when it's in the high one, you can encode as 0. But as I also said in the previous meeting, and we will see also today, we can actually categorize this threshold window with more accuracy. So you can consider 2 bits or 3 bits or 4 bits that we're gonna see soon. And in order to basically erase the flash cell, you need to apply a negative voltage so that move those electrons from the floating gate to the substrate. And then it's gonna be back to the nominal voltage. The threshold voltage is gonna be nominal again. So when you program basically flash cells, you will have basically threshold distribution of cells in a program page, block, or chip. I mean, so you program your flash chip, which consists of several, let's say, I mean, as a kind of quick reminder, each flash chip has can have 1 or 2 or several dies, and each die has several planes. In each plane, we have many blocks, and in each block, we have many pages. So basically, we have kind of this distribution of threshold voltage among the different cells. Which means that basically there are Y cells whose VTH is X. So you can see that basically it's not going to be very, I mean, perfect threshold voltage. So you will have a range for the erased one, for those cells that you consider them as erased, basically that threshold voltage is the nominal one. It's not also very, I mean, one unique value because of the process variation. So you will have different threshold voltage. And at the same time, I mean, similarly, when you program flash cells, or I mean, all those flash cells, you will increase the threshold voltage. But again, this threshold voltage is not going to be only one value. So there is a range for those threshold voltage that you are consider them as program or 0. So this is something that's important to take into account. And the reason for that is basically we have variations across the cells. And some cells are more easily programmed or erased, but some cells are basically hard to program. So you need to basically, in the end, when you apply a program voltage, some cells the threshold voltage is gonna quickly increase, but for some cells you need to apply more, or you need to wait more, basically. So yeah, as we discussed also in the previous meeting and also today, we can have different, we can categorize the threshold window with more accuracy or more, I mean, more fine-grained manner. So here, as an example, we consider that we want to have a TLC cell that we can store 3 bits. So basically, we have with these voltage threshold states, you can basically encode more bits here. So here you can see between any of these two consecutive state, you can have a reference voltage. So it's not like a SLC flash that you need to only apply one reference voltage in order to see if it's program or erased. Here, since the division of this threshold window is more fine-grained, you need to apply several reference voltages to read your data. So as a consequence of that, basically, we can see that the width of the threshold voltage is it's limited now. So that makes it narrower, and that's essentially reduce the margin between two consecutive threshold window. And that you can imagine that why the reliability for TLC flash is lower. Or also you saw that in the previous meetings that basically the endurance for TLC NAND flash chip is basically lower compared to SLC, and that's one of the reasons, because the accuracy in order to read perfectly is higher. You need more accurate read. So, and basically you have lower margins in TLC. So as a result of these things, you cannot use your flash cells for a long time accurately. So when you program a flash chip, after some time, you can see that basically the threshold voltage changes over time after program. So it's going to be, reduced. And it's also important to it's important to note that basically it's not only shifted after program. So threshold voltage is not going to be only shifted. They can also, they're going to be widened after program. Why is that? Because I mean, there are some cells that they lose their charge, I mean, faster than other cells. So in the end, the distribution is going to be different. So yeah, so because it's only was the fact that it was only shifting, you can basically change your reference voltage and easily, I mean, you can recover your read accuracy, but since it is also widening, it at some point you will have some errors, which you need to recover that. Okay, so here, I mean, we have this trade-off basically. So whenever we want to use higher basically densities, I mean, like TLC or QLC flashes, you can have higher density and higher capacity in your flash chip, but at the same time, reliability is lower. But if you want, and also you can also say that the performance is also lower because of the read performance. You will see that it's has lower performance. But basically, if you want higher reliability and higher performance, you need to go with the SLC SSDs, and we have both SSD designs in the market also. Okay. So there is no question over chat. Yeah. So now let's see how we can do basic operations in NAND flash chip. First, consider that we want to program a page. So as we discussed basically in a block, when you want to program a page, you need to apply your voltage, the reference voltage to that target page. So other basically pages that you don't want to program them, you need to apply high voltage that we call them as VPAS, just to make sure that, I mean, they should act as a resistance, no matter if they are programmed or not. So that VPAS should be high enough to turn on them. And then there are also two basically transistors, which, if you remember, that's important for the plane control, that basically which block needs to, or which NAND string is connected to the bit line. So that block that you want to basically program one page in that, you need to apply VCC to those transistors, SSL and GSL, to make sure, I mean, those transistors are on and this NAND string is connected to the bit line. And for that basically page, for that page that you want to program, you need to apply vProgram to that. Okay. So another important thing to know here is that you have this basically bit line control. You can inhibit some cells to not be programmed. So how we can do that? Basically, so for simplicity, for now, consider that we want to basically write SLC. And the data that you want to write, I mean, some cells are going to have 0, some cells 1. And you already know that basically based on the baseline encoding that we were talking about, those cells that we don't program them, which means that, I mean, they are erased, we will consider them as 1. So basically, when you want to program a page, you only need to program those cells that they need to store 0. Otherwise, I mean, you don't program those other cells. So you should have a technique to basically inhibit those cells that you don't want to program. We are actually approaching that with just applying VCC to those bit lines. So whenever you want to program, you also need to have this function to inhibit some cells. And for that, you need to apply VCC to those bit lines. And other bit lines, you would apply ground. And that basically you can program. Okay, so imagine that we are in this position that you want to basically program a page with the data that, I mean, you are seeing here. Initially, all the cells are erased, and we have something like that, right? The distribution of the cells is like that, distribution of the threshold voltage. But when you apply the program voltage, after some point, you would like to receive to this, I mean, beautiful threshold distribution. that some cells in that page now they have 0. I mean, they are programmed and they will be encoded as 0, and other cells are 1. But the reality is that if you apply the program voltage, which is a high voltage, like 20 volts, at the first time, you will reach to something like that. So those cells that you inhibit them, they are okay. But those cells that you want to program them, I mean, this blue curve, you will see that basically you're not very successful to program, to have a very good distribution. Why is that? Because there are some cells that they are easy to program, and when you apply the high voltage, they will easily go, I mean, the threshold voltage is going to be increased more than the reference voltage, but some cells are hard to program. So for them, you need to basically wait more, or you need to apply a higher voltage. So basically, this is what's going to happen. So in order to basically deal with this issue, people are using some technique, which we call it incremental step pulse programming, ISPP. So with this technique, basically, whenever you want to program, you first apply another voltage, which we call it, I mean, kind of V program 0, which is bit, I mean, can be also lower than compared to the maximum program voltage. And so basically, you apply this as a one pulse, and then after that, you evaluate. So when you apply this program 0, you can see that we are reaching to this position. That some cells are now, they are okay, but many of them are still not okay. So basically, after applying V program 0, you need to evaluate and see basically how to evaluate. Basically, you need to read. You need to read the data that is stored in Flash, and basically see what is the story. Is the data that you want is correct or not? So those cells that they are already programmed, like these cells, for example, in the next step, you are gonna inhibit these cells by applying VCC to the bit line. So you are not gonna basically program these cells anymore. So, but other cells, some other cells that they are not still programmed, you need to apply another V program. So the next pulse, you can apply V program 1, for example, and then you can see that you are shifting this curve to the right. And after some time, you will reach to this beautiful distribution. So this technique is very important to to write with good resolution in NAND flash chips. Any questions? Okay. So now let's see how we can read. So by the way, here we only discuss SLC, right, program. The technique for MLC or TLC is also similar to that. The only thing is that you need to have more resolution, and this incremental step pulse programming is going to be a bit harder because you need to basically make sure that the distribution of those basically you will have different distribution, different distribution in that page. So yeah, this is important, but yeah, this is also something important that I will discuss later. But the thing is that in TLC, we don't basically store one page in a TLC page. I mean TLC NAND flash. So since each TLC NAND flash, we have 3 bits in each cell, and in each word line you can have 3 pages. So in reality, what we are doing is that we are storing 3 pages. So one page is basically represented by the most significant bit, the second page with the central bit, and the other page with the least significant bit. So basically, when you want to write the page, depending on which page are you basically programming in that NAND flash chip, you need to basically handle that bit in your distribution, basically. Okay, yeah, but I mean, we are not going to cover in detail how we can program MLC NAND flash chips, but I guess you got the idea. Okay. So now we want to read. here we just first discuss how we can read in SLC, but we also see how we can read in MLC or TLC here, for example. So when you want to read, basically you need to apply V reference voltage. To other basically word line, you need to apply V pass as we discussed. But that page that you want to read, you need to apply a reference voltage to the word line. And basically you need to charge all bit lines to VCC. And then basically depending on the current flow. So those basically bit lines that they have no current flow, you will basically you will encode them as 0. So why they cannot basically flow current? Because I mean the flash cell by applying VREF is off. Why? Because it's already programmed and the threshold voltage is higher than VREF, so you cannot turn on this transistor, and this charge is not flowing. So yeah, and you will consider that as 0. And those basically bit lines that the bit line current, I mean bit line has some current, you will encode them as 1. And they will happen when basically they are erased, because by reference voltage, this flash cell is going to be on and will flow the current. And that's similar to that. But I mean, we will see later in this lecture that how we can sense this current, because I mean, we should have a logic for that also. We will see later. Okay, but now let's see how we can do page read in the MLC, which is a bit more a bit different and a bit more challenging, but it's also interesting to see. So imagine that basically you want to read the central, the CSB bit in a TLC NAND flash. So what you first need to do is just, so based on this the encoding that you have. So here is an example encoding that we basically encode these 8 states to different, 3 bits. So what you first need to do is just check what are those reference voltages that the 2 consecutive states, they have flipping in a CSB or central bit. So we can see, for example, here, voltage reference 1, you are seeing some flipping, right? But for example, reference 2, there is no flipping for the CSBB. So those reference voltage that you have flipping is reference 1, reference 3, and reference 5. So the next step is that you need to apply these reference voltages one by one. So you first apply V reference 5 and you will read your data. So basically, for example, for this one is 1, 1, 1, right? So since the 1, 1, 1 is in this state, when you apply VREF5, you will read 1, right? Because so this basically VREF5 for sure is will turn on this flash chip, and basically we have current in the bit line, and we will consider as 1. But for example, I mean this one, yes, 0, 0, 0. So here again, since you apply VREF5, you read 1, because VREF5 is higher than the threshold state of 0, 0, 0, which is P3. So, but this is wrong, right? We need to read 1 here. So that's important, that you need to apply other reference voltages. And in the end, I mean, somehow combine the sensing values to reach to the exact data that you really read, that you want to read. So we already talked about these things. Then after that, you need to apply reference 3, and you are reaching to these bits, and then reference 1. So you can see that by applying reference 1, in the end, we finally managed to read the correct one for this for this also set. So by applying any of these reference voltage, you will have some value, some bits. And in the end, you need to basically combine these bits that you read to realize that what is the final value. So for this specific encoding technique, it's actually it's proven. You can also work on it as a homework if you are interested. But it's proven that actually if you XOR the value that you already read, you will reach to the final value, to the correct value, basically. So you apply different reference voltages, pi, 3, and 1, and you basically XOR the bits that you read, and in the end, you have the correct bits that is stored in the CSV of TLC flash. Okay. So let's see some takeaway. Basically, bit encoding affects the read latency. Let's see an example. We want to compare the number of sensing for LSB. So as we discussed in the, so here as an example, you are seeing two different encoding, right? The first one is the similar encoding that we had in the previous slide. But the second one is in another basically encoding. So when we want to read LSB, we need to check what are the states, what are the reference voltages that the two consecutive state has a flipping in the bit. So you can see from this figure that here LSB is 1, then is 0. So VREF 0 is one of the candidates. Then we have also here VReference 4. And that's all, right? So here, when you want to read LSB, you need to apply VReference 0 and VReference 4. But the following the second encoding, in order to read LSB, here you have VReference 0. Then again, here VReference 2. Again, here VReference 4. And then here VReference 6, right? So here you need to apply 4 reference voltage. And in the end, you have 4 sensing latency in order to read LSB bit. So basically, now you can see that reading LSB in this encoding is faster compared to this one. But now let's compare the, basically, let's see the most significant bit. So for the most significant bit here, I mean, the first encoding, you only need to apply VReference 2 and VReference 6. But the second encoding, you need to apply only 1 reference voltage. Because all the MSB bits, when they are 1, they are less than, the threshold voltage is less than reference 3. And the remaining is higher than reference 3. So you need to apply only 1 reference 3 to read the MSB bit in this flash, in this encoding scheme. So yeah, you can see actually some trade-off here. So in this basically example, let's clean this slide. So in this encoding, reading LSB bits is faster than the second one, but the second one has faster MSB bits. I mean, read latency compared to the first one. The first one, you have more balanced latency in order to read LSB and MSB. So you see that LSB, we apply only 2 reference voltage, and MSB also the same. But the second item, you have some unbalanced reading, right? So MSB is very fast. You only need to apply 1 reference voltage. Actually, reading MSB bit is, I mean, equal to SLC NAND flash performance. But reading LSB is quite slow. You need to apply 4 reference voltages. So with this kind of trade-off, I mean, people need to deal, and I mean, designers need to basically design and realize that what is the best or optimum way to encode basically NAND flash chips. Sorry, encode the threshold windows. But the thing is that normally, I mean, there shouldn't be the best response to all of these encoding. And I can imagine that different vendors are using different encoding schemes. So with this, let's say the second encoding that we have, since MSB bit is faster, people also consider it as a kind of cache. So whenever we want to have some pages that we want to access them faster, you can program them in an MSP page. But those pages that they are not going to access frequently, you can program them in an LSP page. So basically, different trade-off and design decisions can happen as a result of the encoding. And this is actually one of the interesting research directions. Okay. Any questions? Okay, and no question from YouTube. I guess we can continue. Okay, so we already covered NAND flash page read and write. Let's quickly also see how we can do sensing circuitry. So for the read mechanism, basically NAND flash read mechanism consists of 3 steps: pre-charge, evaluation, and discharge. So in this slide, you can see these 3 basically states: pre-charge, evaluation, discharge. And you can see similar, data here. So we have this reference voltage that we apply to that flash chip or that page that we want to read. And we also apply VPass to other. So, this is another figure, but overall it's the same. But this part is kind of new for you because it's just saying that how we can sense the current into the bitline. So at the first step, which is pre-charge, you need to pre-charge the enable pre-charge transistor to charge all target bit lines and their sense out capacitors, this capacitor, to be pre-charged. So basically you apply this, activate this transistor, and it's connected to voltage pre-charge, and it's gonna basically charge the bit line and also this capacitor to V pre. So after that, you need to do evaluation. For the evaluation, you need to basically first disconnect the bit line from the pre-charge and enable the latching circuitry. So to enable latching circuitry, you need to, make it on. We will see how we will make it on also later. But yeah, and then depending on the, so if this basically, by applying this reference voltage, if this transistor is on, which means that basically we don't program this flash cell, basically this current is gonna be flow, and this capacitor will be discharged. And if this flash cell is already programmed, it's not gonna flow any current, and basically your capacitor is gonna be, will remain charged by the end of this process. And and after evaluation, you need to discharge. For discharge, basically, your bit lines are discharged to return the NAND string to its initial state for future operation. And you need to turn off the latching circuitry. Okay. So, but now let's see the internal circuit for latching circuit. So before the evaluation step, the chip initializes the latching circuit also. So here, when we say that pre-charge, we only talk about the capacitor, but we also need to initialize the latching circuit. How we initialize the latching circuitry? We need to activate transistor. So here you can see there are 2 basic in this latching circuit. This is the back-to-back NOT, which is, you know that it's kind of latch. And then we have also these 2 transistors, M1 and M2. And these transistors are also connected. And there is also here a transistor that is controlled by the SO, which is this capacitor basically. So the gate of this transistor is controlled by SO. So in order to basically initialize the latching circuitry, you need to first activate transistor M1. So by activating this M1, you are connecting. So also remember that when in the pre-charge state, you also activate this M pre. And since V pre is going to be stored in these capacitors, and since high enough, this transistor is also going to be on because you are applying the high voltage to the gate of these transistors. And then, so when you also activate transistor M1, essentially you are connecting this node to the ground. So then as a result, the V out bar is going to be 0. And V out, and because of this back-to-back NOT, V out 1, V out is going to be 1. So this is the initialization step for the latching circuitry. So in order, when you want to evaluate, so you already saw that how we evaluate, right? So we need to disconnect the pre-charge and then see how this the capacitor is remains the charge or discharge, basically. So we need to disable pre-charge and enables M2. So we need to disable both pre-charge transistor and also these M1, and then we need to apply. We need to enable M2 transistors. Now we have two different states depending on the the bit line and the flash cell that you want to read. So if that flash cell in the bit line basically is not programmed, and it's erased. So when you apply, that VREF is gonna connect this bit line to 0, right, to the ground, and because of that, this capacitor is gonna, will be discharged. So this will be discharged, and this transistor will be off, right, because there is no high voltage in the gate. And since you already and you also enable M2, right? So this transistor is on. But since this one is off, there is no connection to the ground. As a result, these two nodes, V out bar and V out, they will basically remain their charge that we had in the previous state. And in the end, you can see that V out is 1. So you also want to read 1, right? Because that flash cell was not programmed, and we encode that state as 1. So we are reading 1 here. However, if this NAND flash cell is already programmed, so the flow is not going to be changed. It's not going to be flow. So this capacitor will remain its charge. And so this transistor will be on. And since you also enable M2, there will be a pass between out and the ground. So this out, it will be moved to 0. And this back-to-back NOT will make this out bar to 1. And you are reading 0 here, right? Any questions? Okay. So an interesting point here is that basically you're also able to do inverse read with this sensing circuitry. And with that, basically, you can also easily enable NOT operation. So in order to do inverse read, the meaning is that inverse read is that when you store 1, you read 0. Or if you store 0, you will read 1. So you need to just changing the activation sequence of M1 and M2. So in the pre-charge state, we activate M2. And in the evaluation state, we disable M2 and activate M1. And with that, you will easily read inverse of your data. So I will let you work on it as a homework because it's easy, similar to what we had here. But yeah, you will see when you first apply M2 and then deactivate M2 and apply M1, how it's gonna change. But in the end, you will read, you will see that we will read the inverse data. Okay. So yeah, I already mentioned that we can actually enable NOT with this inverse read. And there is also this paper that we will cover in our lectures later, Flash Cosmos. that essentially what we did here is using, we show that if you activate or sense multiple word lines together in a SLC NAND flash, we in the previous slides, we just consider the case that we only apply one reference voltage, right? So, but if you apply several reference voltage or activate or basically, or you want to read, sense multiple word line at the same time, essentially you will have a kind of AND operation or operation, depending on those word lines are inside one block or they are between blocks. So, and also with this inverse read, we can also implement NOT. So basically in Flash Cosmos, we show that how we can do basically in Flash bulk bitwise operations using inherent computation capability of NAND flash memory. And we implement AND or NAND, NOR, XOR, XNOR, and also many more different gates as a combination of these AND and OR. So we will cover this paper in a different lecture in detail, but I just like to give an idea about how we can use this sensing circuitry to implement different logics. Any questions? Okay, so if there is no more question, I guess we can wrap up today's meeting. There are some materials that we already have them in our website. We are it's good to take a look at them and read and improve your knowledge in NAND flash SSDs. Okay, thanks a lot, everyone. And I guess we will see you all next week in another lecture of PNS SSD. Take care and have a nice weekend.
Thank you.